Namaste dosto. Imagine you're watching a train approach a station. It gets closer and closer, but maybe the doors open right when it stops exactly at the platform. This idea of getting closer without necessarily touching the exact point is what mathematicians call a asterisk limit star. So, what exactly is a limit? Simply put, a limit describes how a function behaves as its input value moves asterisk closer asterisk to some number. Importantly, the function's input doesn't have to actually reach that number. It's about the value the function tends to or approaches as the input gets nearer. Mathematically, we write this idea as the limit of f of x as x approaches a. This looks like the statement, limit as x tends to of f of x. Here, the function f of x approaches some value as x moves toward the number a. Why are limits so important? They form the backbone of calculus because they help us understand instantaneous change, like how fast a car is going at a precise moment, and a continuity of functions, which tells us whether graphs have breaks or jumps. Picture a smooth curve on a graph with the x-axis and y-axis labeled, and see how the curve approaches a point labeled A from both the left and the right sides, steadily moving toward a certain height on the y-axis. This is the perfect visual of a limit in action. Keep this image in mind, because understanding how functions behave as inputs asterisk approach asterisk values will illuminate so many interesting areas in mathematics ahead. Now, let's deepen our understanding by looking at what happens from each side of the point where x approaches a number. Imagine you have a little ant walking along a number line toward point A. If it comes from the left side, meaning from values smaller than A, we call the value that f of x approaches the asterisk left-hand limit star. We write this as limit of f of x as x approaches from the left, or mathematically, limit as x approaches a minus. Similarly, if the ant approaches from the right side, values larger than the corresponding value f of x approaches is the asterisk right-hand limit asterisk, written as limit as x approaches a plus. For the overall limit at a to exist, both these one-sided limits must be equal. In other words, the function's behavior as x nears must be the same whether x comes from the left or the right. In math, if the left-hand limit of f of x as x approaches is equal to the right-hand limit of f of x as x approaches a, and both equal some number L, then the limit of f of x as x tends to a is also L. Visualize a graph showing a function with different behaviors when coming from the left and right of a point A, marked clearly with LHL and RHL. This helps us see exactly when the overall limit exists and when it doesn't. Understanding these one-sided limits is crucial because sometimes the function might jump or behave differently on each side, so the limit at that point doesn't truly exist. Alright, now that we know what limits asterisk are asterisk, let's see how to find them using algebra. The first and simplest method is direct substitution. Plug the number you're approaching, say, straight into the function f of x. If the function is continuous and well-defined at a, this will give you the limit. But what if substituting causes a tricky expression, like 0 divided by 0? This is called an indeterminate form, and direct substitution won't help here. In such cases, algebraic simplification comes to the rescue, with techniques like factorization or rationalization. For example, consider the limit as x approaches 2 of the function x squared minus 4 over x minus 2. Written mathematically, limit as x approaches 2 of x squared minus 4 divided by x minus 2. At first glance, substituting to gives 0 divided by 0, that pesky indeterminate form. But notice that x squared minus 4 factors into x minus 2 times x plus 2. So the expression becomes limit as x approaches 2 of x minus 2 times x plus 2 divided by x minus 2. The x minus 2 terms cancel out, leaving the limit as x approaches 2 of x plus 2. Now, substituting x equals 2 directly gives us 2 plus 2, which is 4. This means the limit exists and equals 4, even though the original function was undefined at x equals 2. Picture a graph showing this behavior, with a tiny hole right at x equals 2, meaning the function is not defined there. but the curve approaches the value 4 from both sides. So, algebraic simplification turns the indeterminate into a neat value. Let's build on that idea with another example highlighting asterisk removable discontinuity star. When direct substitution again gives the indeterminate form 0 over 0, factorization can often help by revealing common terms that cancel out. For instance, take the limit as x approaches 3 of x squared minus 9 divided by x minus 3. Written mathematically, limit as x tends to 3 of x squared minus 9 over x minus 3. We recognize x squared minus 9 as a difference of squares, x minus 3 times x plus 3. This changes our expression to the limit as x approaches 3 of x minus 3 times x plus 3 divided by x minus 3. Cancel the x minus 3 terms, and the expression reduces to the limit as x approaches 3 of x plus 3. Substituting x equals 3, we get 3 plus 3, which is 6. Now, the interesting part. Even though the function is undefined exactly at x equals 3 because of division by 0, the limit exists and equals 6. This is called a removable discontinuity. The graph has a hole at x equals 3, but the curve around it is smooth. Visualize the graph with a small hole at x equals 3, with the curve smoothly passing near y equals 6. Knowing how to remove such discontinuities by factorization helps us find limits and understand function behavior better. Now, what if the function involves square roots, leading to that tricky 0 divided by 0 situation? We use asterisk rationalization asterisk, a trick where we multiply numerator and denominator by the conjugate expression, which helps simplify the surd terms. Consider this example. The limit as x approaches 0 of the function square root of 1 plus x minus 1 divided by x written mathematically. Limit as x tends to 0 of square root of 1 plus k smiley minus 1 all over x. Direct substitution again gives 0 over 0. So we multiply the numerator and denominator by the conjugate of the numerator, square root of 1 plus x plus 1. This turns our expression into the limit as x approaches 0 of square root of 1 plus x minus 1, square root of 1 plus x plus 1 are divided by x times square root of 1 plus x plus 1. The numerator becomes a difference of squares, 1 plus k smiley minus 1, which simplifies to x. So the limit simplifies to the limit as x approaches 0 of x divided by x times square root of 1 plus x plus 1. We can cancel x in numerator and denominator, leaving limit as x approaches 0 of 1 divided by square root of 1 plus x plus 1. Finally, substituting x equals 0 gives 1 divided by square root of 1 plus 0 plus 1, which is 1 over 1 plus 1 or 1 half. Visualize the graph of this function near x equals 0, showing the curvy behavior influenced by the surds. Rationalization is a neat algebraic tool for handling limits involving roots. Shifting gears a bit, let's explore what happens to functions as x becomes very large, either positively or negatively. Limits at infinity describe the asterisk long-term asterisk behavior of functions, how the function behaves as x tends towards infinity or negative infinity. For example, consider the simple function 1 divided by x. What happens as x goes to infinity? The function values get smaller and smaller, approaching 0. Mathematically, limit as x approaches infinity of 1 over x equals 0. Similarly, limit as x approaches negative infinity of 1 over x also equals 0. To handle more complex rational functions, we compare the degrees of polynomials in numerator and denominator. The highest degree terms coefficients and exponents determine if the function flattens out towards a horizontal line or grows without bound. Picture a graph of such a function, with the curve flattening out as x increases, showing its asymptotic behavior. Understanding limits at infinity helps us predict how functions behave far away from the origin, an important concept in calculus and beyond. Let's put all this into action with a complete example. Given the function f of x equals x squared minus 1 divided by x minus 1, Find the limit as x approaches 1. First, write the function. F of x is x squared minus 1 divided by x minus 1. Notice x squared minus 1 factors into x minus 1 times x plus 1. So, f of x can be rewritten as x minus 1 times x plus 1 divided by x minus 1, where x is not equal to 1. We cancel the common x minus 1 terms, reducing the function to x plus 1. Now, applying the limit as x approaches 1, substitute 1 into x plus 1, which gives 2. Therefore, the limit exists and equals 2. Visualize a graph with a hole at x equals 1, but the curve smoothly tending toward the value 2. Shabash! You successfully evaluated the limit of a rational function involving a removable discontinuity. Let's quickly recap today's journey through limits. The notation, limit as x approaches of f of x equals L, means the function values get closer to L when x gets closer to A. The limit exists only if both the left-hand limit and right-hand limit equal the same value L. To find limits, especially when direct substitution leads to indeterminate forms like 0 divided by 0, we use simplification techniques, factorization, rationalization, and algebraic rewriting. Remember, a limit captures asterisk approaching behavior asterisk. It's about what value the function gets near, not necessarily its value at the point. One-sided limits also help us understand continuity and whether functions jump or are smooth. And limits at infinity tell us how functions behave in the long run, leading us to understand asymptotes and graphs better. Soch ke dekho, whether it's car speeds, train arrivals, or cricket scores approaching target values, limits give us the mathematical language to describe getting closer in so many real-life situations. Keep practicing these ideas. Mastery of limits will build a solid foundation for all future calculus concepts.